All right, welcome back to Organic Chemistry. We're preparing for our exam, which is on Wednesday. Okay, look to the homework for the style of questions. It's going to be multiple choice questions, just like last time. It's going to be on Top Hat. So please go directly to Top Hat. I will live monitor on Wednesday if you're having trouble getting in. I have a couple ways of doing backup exams, example, so that you just need to make sure you communicate me. Don't stress about it. Just email me and we're gonna get you into that exam and get as much knowledge out of your head onto the computer as possible. Okay, so today we have our group activity. What I'm gonna do is I'm gonna do about a short lecture, and this is kind of instructions. I don't monitor through Zoom. I actually I have Proctorio has an interface that tells me who's taking the exam, how many, whether they're answering questions or not, and your emails are telling me whether or not you've gotten in successfully or not. So I can see who's done, who's actually taking the exam and stuff like that. And when people are done, if they're shown as suspicious, I can go and review the video. But yes, you can, if you're not here for the whole group, just turn it in by midnight and that'll be fine. Okay. So I think that answers all the questions currently in the chat. So let me go ahead and share my screen and start talking about the group activity and the way to think about chapter 6 and 7. Okay, we have four mechanisms that we're playing with, right? We're going to make a substitution product, or we're going to make an alkene, but there's a pattern to it. There's a way to figure out which is which and what your major products are. And that's what I want to talk about today. So let me go ahead and share my screen. There we go. I'm going to go ahead and move this one over here. Okay. So what we have is competing mechanisms, right? And we need to find a way to ask the right questions to determine what our major product is going to be. Okay, so let's talk about that. So when we have our system here, we want to think about, is it a base? Is it a nucleophile? Is it a strong base? Is it a weak base? You want to start comparing things, okay? So if something is a strong base, it can act as a nucleophile or as a base, depending if it's small enough, okay? So think of strong, small bases can produce substitution product, okay? But good nucleophiles that aren't strong bases don't make elimination products. So we need to be able to tell the difference between a strong base and a good nucleophile, okay? So that's very important. And I have a table for you. You need to devote these to memory, and then it'll start to make sense when you start figuring out your more likely products. Okay. Now, if you don't have a strong base and you don't have a good nucleophile, then you must go through your carbocation intermediate. And when you go through your carbocation intermediate, because it's going to be a poor nucleophile and a weak base, you're going to have those in competition. So you need to understand what a weak base is at a poor nucleophile. Notice, when you have a strong base, there's two kinds of strong bases, a small strong base and a big strong base, okay? When you have a big strong base, it acts only as the base. When you have a small strong base, it can act as a base or a nucleophile. So you need to be able to reconcile that in your head about which is which, okay? So we can only form a total of 4 different products from here. Two of them are going to be the same. The E1 and E2 are going to be similar. Okay. Remember, in our eliminations right here, we're going to look for the size of the base to tell you whether you have the thermodynamic product, the more substituted product, or the kinetic product, the less substituted product. Those are the Hoffman products and the Zaitsev products. Make sure you have that clear in your head as well. And I'll help you decide which is which as we go through this set of slides. Okay, so the first thing we have to do is think about nucleophilicity. Okay, things that do not have strong conjugate acids only act as nucleophiles. Okay, so let's talk about some of those things that can be nucleophilic. Water and the OH. Now, in both cases, the water and the OH, The lone pair is the part that's doing the nucleophilic attack, right? The lone pair. Notice all the rest of them have a negative charge. That negative charge is also residing in a lone pair. So if you have a negative charge, you're going to think the more negative that charge is, the stronger the nucleophile is. Okay, so nucleophilicity is just that kinetic value of how fast it's going to react. Okay, basicity, on the other hand, is different. Basicity, we need to pay attention to what the pKa of the conjugate acid was. And notice the order in which these show up now. It's in a different order than the nucleophilicity, okay? So in the case of these bases here, the hydroxide and the alkoxide are our strongest bases. Think about that, because they were, water and alcohol as the conjugate acids, and those are in the pKa range in the 15 to 16 range. Okay, then cyanide, and then our neutrals, water and an alcohol, are more basic than our halogen anions. Remember, our halogen anions are really, really strong conjugate acids. Therefore, that makes them very weak bases. Okay, so that means that nucleophilicity and basicity are different. Nucleophilicity is a kinetic property. Basicity is a thermodynamic property because it's in equilibrium. Okay, so taking that into mind, we can actually increase the rate of E2 reactions by using really strong bases. Okay, the amide ion is stronger than the alkoxide ion. And when you have those really strong bases like that, you are going to increase the amount of E2 product. Okay, when you have weak ions like the chloride or the acetate ions, start thinking of it as more of an SN2 product. They're not good bases. They're not going to make elimination products. And so that gives rise to our SN2 products, because they're still anions. So it doesn't have to wait around for the carboxylic acid. So it does the bimolecular reaction or the SN2 reaction. Okay, so because of this polarizability, the polarizability on them, like especially think about our nucleophilicity on this thing here, we have the iodine as a strongly nucleophilic. Part of that is because of the polarizability, okay? And when we have something like an iodine come in, it can nestle into the 180 degrees from our leaving group and get into that stronger interaction, because it can polarize to get in between substitutions to make that system. So when we have something that is a poor base, we should not see any elimination products. When we have that polarizable nucleophile, we should only see substitution reactions. Okay. So you might think iodine, it's pretty big, but think about it. It can pull some of its electron density, making it a little bit smaller just to fit into that little pocket made by the transition state between your initial starting point, your transition state, and then flipping the umbrella to give you the reverse side. Okay, so polarizability, and if it's a weak base, it's going to give you SN2 products. Okay, now let's look at the size of the nucleophile base. Okay, when you have a small base, hydroxide, alkoxide, methoxide, or ethoxide, those are what we call small unhindered bases. Okay, when they're small and unhindered, they are going to act as a base, but because they're small and because they have that charge on oxygen, they are more likely to act as nucleophiles. Okay, they're still strong nucleophiles. We saw that before, and they're strong bases, but they're small enough that the kinetic reaction goes first. Remember, nucleophilicity is a kinetic. Basicity is a thermodynamic or equilibrium. Now, what if your base is too big? What if you have the T-butoxide or something else? It can no longer act as a nucleophile. It cannot get into the pocket, okay? And therefore, your major product is going to be your elimination product. Okay. Now, in the case of this example here, we actually have a primary alkyl halide. And so when you have a primary alkyl halide, you can get a little bit of SN2 product, but it's the minor product. When it's big and bulky, it predominantly acts as a base because it can't get into that pocket to form that SN2 transition state. Therefore, it predominantly acts as a base. Okay, so we all see the difference between the size of the base and its primary reaction products. Okay, so, and again, this has everything to do with asterics. It can't get that pocket in there, but it can, instead of trying to form the bond here with the atom with the leaving group, it's much closer to just removing one of these 4 hydrogens. When it removes one of those 4 hydrogens, it can make the alkene. And that's why the E2 is our major product. That's how to think of it, as really big, and the hydrogens are much more accessible than trying to form that sigma bond with the carbon with the leaving group. Okay. So if we think about the relative rates of this, okay, when we're thinking about our small base acting as a nucleophile, it's going to act very quickly, okay, and give us our substitution product. Okay. When we're talking about our big bulky bases, it's acting as a base. Therefore, it's going to give us a slower reaction, even for the elimination products. I mean, for the substitution products, because very few of those molecules will have the energy to get right in there and do that substitution. So it's much, much slower. Okay. So our smaller ions are more nucleophilic and are faster than our larger ions. Okay. So shouldn't bulkiness affect base strength? Well, no, because remember, nucleophilicity is a kinetic experiment. Basicity is an equilibrium experiment. Therefore, it actually doesn't change because it'll meet that equilibrium at the same thing, at the same time. It gets to an equilibrium and stays there. So it actually doesn't tend to affect the basicity based on how big you are, because we're not worrying about doing it quickly. We're worrying about finding a nice thermodynamic equilibrium. All right. So that brings us to the concept that nucleophilicity is different than basicity. And again, nucleophilicity is the kinetic product, meaning smaller the concentration of the 2 reactants make it move much, much faster. Okay. Whenever we did acids and bases, we said that there's an equilibrium there. We calculated that equilibrium constant. So what's going to happen is things are going to happen real quick, and then they're going to find some balance between your conjugate acid and your conjugate base, and your acid and your base. And that's where that concentration is going to stay. Okay, that means basicity is your thermodynamic idea here. So a nucleophilicity is our kinetic product. Basicity is our thermodynamic product, okay, or an effect. Okay. So how can we have a base that can't act as a nucleophile? The way you have a base that can't act as a nucleophile is you make it so big that it can't form that new sigma bond with your substitution product. And when you make it so big that it can't form that substitution product, they become non-nucleophilic. Even though each of these has an anion, which you'd think would make it a good nucleophile, the sterics inhibit it from acting as that nucleophile. It needs to wait for the equilibrium reaction. And if it's waiting for the equilibrium reaction, it's going to act as a base. So all of these large anions here are so sterically dependent, they always act as bases. They hardly ever act as nucleophiles. They would never be a major product in a reaction. Using them as a base would always be the major product in a reaction. Okay? And that kind of makes sense. You know, you just have to wait around until you can pull off a proton, and then that of course, cascades down into your elimination product. All right, so what that leads to is this right here. This is a page you should spend a little bit of time making sure you understand why, okay? Weak polarizable bases mainly react in SN2 reactions, okay? So notice that in that table of, in that list of nucleophiles before, I had hydroxide and alkoxide up there, but those are really strong bases. So all of our nucleophiles, except for those two, mainly produce SN2 products on primary and secondary substrates, okay? Tertiary, it's kind of hard, and tertiary doesn't do the SN1. Okay, when we have strong bases like alkoxide and hydroxide, that promotes our bimolecular reactions because they're strong and small, and we're going to get a competition between SN2 and E2. It's acting as a nucleophile and it's acting as a base. Therefore, you're going to get both products. So whenever you see a hydroxide or an alkoxide in a reaction, you want to draw two products, okay? Now, when you have those big bulky bases, they are no longer nucleophiles. Big bulky bases only act as bases and give you an E2 product. In addition, they give you the Hoffman elimination product because if it's harder to get them into the hydrogens close to the more substituted hydrogens, so it's going to go for the less substituted hydrogens. Okay. And then things that are not good nucleophiles and are not good bases, meaning neutral molecules of alcohol and water, okay, they promote mononuclear reactions. Remember, when we had stuff with water and alcohol, those support carbocation formation. Water and alcohol support that carbocation. That means they will be able to support it in an SN1 or SN2 because the first step in both of those is the formation of that carbocation. And you will always have a competition between the SN1 and E1 products in things like water and alcohol. Okay. So if there's no other nucleophile there but a neutral water or alcohol, think carbocation, think E1, SN1, and you have to draw both products. All right, questions on that? Now the next slide, I think, is one you need to know, okay? This is a good study guide slide, okay? So notice I have, starting out here, strong underhindered bases are good nucleophiles, okay? So you're gonna have a lot of SN2 products. Strong bulky bases are poor nucleophiles. It'll only act as a base. Good nucleophiles that are weak bases are gonna do substitution products, mainly SN2. Weak bases are going to kind of do a little bit of both, and I'll talk about that in a minute. And then the weak bases that are neutral molecules or mono-deprotonated acids, multi-proton acids, act as poor nucleophiles, and weak bases start thinking SN1 and E1 reactions, always forming that carbocation. So now let's do it by halogen type, okay? So by halogen type, our strong bases, okay, are good nucleophiles. So we expect a methyl group and a primary to produce substitution products as their primary products. They're small and it's easy to get to the primary and the methyl halide. It's easy to get into that transition state. So you're going to have those as major products. However, it's still a good base. So you're going to have a little bit of elimination once you get to the primary. You are not going to have any elimination in the methyl. There's no hydrogen adjacent. It cannot do that. Now, once you get to secondary, sterics are starting to take over and E2 becomes your major product, okay? But SN2 is still a minor product because it's still a secondary and it's still small, okay? But now notice how the product ratio is flipped, okay? And then your tertiary will not undergo a substitution reaction most times. It'll be a very, very, very minor product. So we can say this 100% E2. All right. So is this making sense? If it's small and a good nucleophile, have a primary, secondary, you're going to get the substitution product. As you start getting steric demand, you're starting to see elimination products become primary. Okay. All right. So now let's switch to become big bases. Well, big bases are not going to be very nucleophilic, but in the case of methyl, it can do that because it cannot do an elimination reaction. The only reaction it can do is that substitution reaction. Okay. However, on all other substrates, your E2 is primary. Okay. So on your primary, is your major product. Primary, secondary, and tertiary. However, you can get a little bit on a primary because it's not too sterically hindered yet. But by the time you get to secondary and tertiary, it's always the elimination product. Okay, and it's that E2 elimination product. Okay, so with our good nucleophiles, but not very basic, we're going to see our substitution product being major until we get sterically hindered in our tertiary. Once we get sterically hindered in our tertiary, we now have to go through the carbocation, and we have a mixture of SN1 and SN2. So good nucleophiles are always our major SN2 products. Okay. Now, weak bases, poor nucleophile, don't react with methyls, don't react with primaries, and give a mixture of carbocation-based products in secondary and tertiaries. Remember, we can't form a carbocation here, we can't form a carbocation here, and this is not nucleophilic enough to even try to do an attack. Okay. So we have to think about the size of the base, the nucleophilicity of our product, of our thing, and then whether or not we have a methyl, primary, secondary, or tertiary. So, questions on that? Okay. All right. So, this is great. I love this table. I don't understand it, but when I get in to look at the problem, I don't know where to start. Okay. Here's how to attack the problem. Okay. You look at the problem and you say, okay, I need to figure out a few things to start with. Okay. So when I start, I need to look at where are the charges. Okay. Because the charges are going to tell me where our attack sites are. It'll tell us something about the nucleophile. It'll tell us something about the electrophile. Okay. Notice I said put delta and full charges. Delta is like for an alkyl halide, there's going to be a partially positive charge on that carbon and a partially negative charge on that halogen, because that halogen wants to be the leading group. So we need to put our full and partial charges on there, and now you know what's going to attack what. The nucleophile is going to attack the electrophile, and it's going to do something, okay? Now, you also want to identify if you have a chiral carbon. Because remember, SN2 reaction, you're going to do an inversion of chiral center. SN1 reaction, you are going to scramble the chiral center. The second thing you do is you figure out which is the nucleophile or base and which is the electrophile or the acid. Okay. So remembering what strong bases were, the alkoxide and the hydroxide, or the T-butoxide, etc., tells you you have a base. The other things with charges on them are going to be nucleophiles. And the things that have no charge on them are going to be the ones that have to go through that unimolecular carbocation. Now, we know what's going to attack what. We know what's going to attack where. We know whether it's going to attack as a base or a nucleophile. Okay. Now we have to figure out what's going to be our product. Are we going to do a substitution or are we going to do an elimination? That's where we go to primary, secondary, tertiary, allylic, benzylic, aryl, and vinyl. Okay. So we talked about that where primary and secondary are going to favor substitutions. This is going to favor elimination. These are going to favor substitutions, and these aren't going to do anything at all. Okay, that's in the part 1, and that's in chapter 6 too. So go review that. So now you know what's going to happen. Now you know you're going to have substitution reactions, SN2 reactions here. You know, you're going to have E1, E2 reactions here. And you know that you're going to have faster things happening on these other substrates. All right, so now you say, okay, is it a strong or weak base? Is it a hindered or unhindered base? Because now you have to decide whether it's acting as a base or not. If it's acting as a base, is it small enough to act as a nucleophile, or is it too big to act as a nucleophile? And you have to react it as a base. Okay. Next thing you do is you calculate, is it a good or bad nucleophile? Okay. If it's a good nucleophile, it's going to act as a nucleophile. If it's a poor nucleophile, it might act as a base. Okay. And then the last thing you do is look at the solvent. If it's in a protic solvent, you can support a unimolecular E1 or SN1 reaction. If it's an aprotic solvent, it cannot support that carbocation, and therefore it must be doing an SN2 or an E2 reaction. Okay, so again, you don't have to do it in exactly this order, but this really helps you kind of down select, saying, okay, it can't be E1, it can't be SN1. All right, I'm down to two things. Is it small? Is it primary, secondary? That's how you can talk your way through it, knowing exactly how each thing happens. So let's do an example. Okay. After that, you should be able to determine that what is going to happen or not. And then if you decide it's going to happen as an elimination reaction, you have to decide your alpha and beta hydrogens and then figure out your regiochemistry for your reaction. Is it going to take the Hoffman product, or is it going to take the Zaitsev product? Excuse me. And always remember, no reaction is also an option, i.e. methyl halogen with water. Nothing happens. Okay. All right, so let's talk that same process through two examples, and then we're going to go to our group examples, which is 8 more of these, okay? So if I just showed you this reaction here, okay? First thing you should say is acetone. That's a polar aprotic solvent. So no E1, no SN1, done. All right, great. Now we have one thing down. Number 2, we have a sulfur anion, okay? All right, we have a sulfur anion, and we know that to be a good nucleophile, but not one of our strong bases. And we have a primary halide, okay? So we can't go through a carbocation. We have a good nucleophile, and we have a good, we have a primary non-hindered alkyl halide, okay? So let's go through the steps again. Let's add our charges, okay? We know that this is going to be our anion right here because sulfur likes to have that, oops. Okay. So sulfur is our anion right here. And see, if that's why I actually have you assign where the anion is, because this looks like a neutral species up here, but you know that sodium's carrying the positive charge, that means the sulfur's carrying the negative charge. And when we do our partial charge here, we can see that our nucleophile is going to be attacking here, okay? So we know what our nucleophile is, we know what our electrophile is, okay? All right, we also know that our nucleophile is a good nucleophile and our electrophile is a primary. Whenever you have an unhindered primary group with a good nucleophile, you're going to favor SN2. You're going to have the substitution product, okay? This is not a very strong base, so you're probably not going to have any E2 products. And we have a very polarizable negative charge here, which means it's definitely going to go in the substitution reaction. And we have an aprotic solvent, which says we have to go through an SN2 reaction because we can't form that carbocation. So that means our major product is going to be our substitution product plus sodium bromide. You typically don't have to show the counter ion. We want to show the substrate, the organic compound. All right, questions on that? Notice I didn't use every single one of those rules because we figured out it wasn't a base, so we didn't have to figure out how strong, whether or not it's going to do an elimination reaction. Okay. All right. So that means that our final product is going to be our substituted material that I just drew there. Oh, sorry, SM. And if we want to continue down the path, we have a good nucleophile attacking an unhindered primary alkyl halide, which means SN2 again. We are going to have very little E2 because it's not as strong a base as the alkoxide or the oxide. And the bromide ion is a good leaving group, so that means it's going to happen fast too. So, okay, questions on that? So you don't just look at the thing and say, oh, well, it has to be this. Go through the different steps saying, is it primary, is it secondary, is it tertiary? Is it a good nucleophile? Is it a good base? What solvent is it? Okay, those things right there are going to give you a really good idea of how to figure out one from the other. Okay, so let's do this. We have chirality here. All right. And we have, first thing we have is a secondary alkyl halide, okay? We have alkoxide, so we have a small, strong base. And we have it in a protic solvent. All right, now we can have a bunch of things happen to us, right? So let's start thinking about where the charges are. The first place of where the charges are is we have it on the oxygen, has a negative charge on it. Our secondary carbon here has that partially positive charge on it. So what we know is that our secondary is one of those that can undergo a bimolecular reaction or a unimolecular reaction because it can stabilize that secondary carbocation. So we haven't eliminated anything yet, okay? So now let's talk about the nature of the nucleophile. Our nucleophile is the alkoxide, okay? But that's also a strong, unhindered base, okay? So it's a good nucleophile and a strong base. Okay? Even though the solvent can promote a carbocation, remember, our substitution, our bimolecular reactions are much faster and therefore are going to be the predominant products. So we're either going to have an SN2 or an E2 as our primary product because they're faster than forming a carbocation. Okay. Because it's unimolecular, it doesn't have to wait around for that carbocation to form. Okay. So what's going to happen? Well, we have both a strong base and a good nucleophile. We have a secondary, so it really can undergo both an elimination reaction and a substitution reaction. So I think we have to draw two products here, okay? And I think we're gonna have to show that we have an oxide coming in as a substitution product, okay? Iman, do you have a question? Your mic's on. Okay, sorry. Okay, so let's draw our substitution product first. And because it's an SN2, we didn't wait around for a carbocation because we had a good nucleophile. What is our stereochemistry going to be? So because it's an SN2, we always have inversion of stereochemistry. So that means we have to have a wedge here because we had a chiral carbon with an OM ion. So that's one of our products, okay? What is our second product? So we had this dashed wedge here. Told me it was going back, which means the methoxide has to come from the front, which gives it a solid wedge here. So that's going to be our stereochemistry of that wedge. So are we going to eliminate, let's go ahead for our E2 product. This is our SN2 product. For our E2 product, where are we going to take that proton off? We have this secondary proton and we have this primary proton. They're both alpha protons. We're going to take off the secondary or the primary. Okay. To figure out which one we're going to do, look at the size of the base. Okay. It's a very small base, meaning it's going to make the thermodynamic product. The thermodynamic product is going to be the one with the internal double bond. So our major elimination product is going to be our trans alkene. Remember, trans alkenes are more stable than cis alkenes, which are more stable than primary, with mono substituted here. So in theory, we could have 3 different elimination products, and right here. However, the major one is going to be the more thermodynamically stable one. So these are going to be your 2 competing reactions right here. Now, if you wanted one over the other, what's the one trick we could do here? Do we want to run this if we wanted the SN2 product, do we want to run it hot or cold?
Cold. Cold,
right, because the elimination products are favored in warmer solutions. So our primary product, because we don't say anything about temperature here, is going to be our SN2 product, with our E being our minor product. Now, if I went over here and said 100 degrees, oops, 180, just 100 degrees, that means our E2 product will become our major product, and our SN2 product will become our minor product. So that's the last thing we look for here. All right, questions on that? So here are all of the products drawn out for you. Our SN2 product, our E product, and our E product. Now, and this right here, this is our minor product because of the fact that it's going to act as a strong base first and a nucleophile second. So all of these products are going to be our major product, with our cis being the primary, sorry, the trans being the most. So this is going to be our highest yielding product. This is going to be our minor product. Okay, and that is telling us why those things are. Questions on that. So use the steps, figure out what should be attacking what, and then figure out which mechanism you're favored or not favored with. Okay. So let me actually stop sharing my screen. And I need to share this. All right, so are there any questions? So I know this is just as clear as mud right now, but that's what the activity is for, so we can get to this. So I'm gonna go ahead and share my screen here. Share my screen, and it's going to be Acrobat. All right, so you should see this. This is the instructions for the activity, okay? I'm giving you a few of the slides we just went over so that you can kind of start using them as a reference and start getting familiar with, is it a good base? Is it a good nucleophile? Is it a bulky base? Is it a weak base? And what to look for in reactions, okay? I also gave you this table here. This is something you need to kind of know and understand. And so for those who like to memorize, but for those who don't, go and look at those general trends. Is it polarizable? Is it bulky? Is it a good system? Okay. And then don't forget the role of the nature of the alkyl halide. Methyls, you know, can't do elimination reactions. Primaries will give you substitution products, or unless there is a good bulky base, then it's going to give you elimination products. And then look at your tertiaries with weak stuff is always going to give you a competition between SN1 and E1, because you have to wait around for the alkyl halide to form. I'm sorry, the carbocation. All right, so on the thing here, I have an example. I'm going to give you a list of reagents here and a solvent, and you need to figure out what the major and or minor products are, okay? So in this case, we have this acting as, we have a T-butoxide. We know we have a negative charge here on that oxygen. We have a methyl halide, and we're doing it in a protonated solvent, okay? So the only reaction we can have here is a substitution product. Because we have a methyl halide, it doesn't undergo SN1 reactions, it only undergoes SN2 reactions as per our list here. So that means our only product is our substitution product. We cannot do an elimination because there's no alpha hydrogens. There's no alpha hydrogens, we can't do the elimination. We only get one product, okay? So what I want it to look like is when you draw it out, you can do, this actually has all those steps there. We drew our anions. If it acted as a nucleophile, we have one set of products. If it acts as a base, it acts as another set of products. And then you can tell which one does or does not go, okay? So this is what I want to see to turn in is basically this drawing right here where you have what is the nucleophile, what is the substrate, and then what your major and minor product are, okay? And then once you do that, go ahead and upload it to Canvas before midnight. If you have to leave early, that's fine, go ahead and just get it done. If you weren't in class and you're looking at this later, just get it turned in by midnight, okay? We have 66 people, so we're gonna do, okay, that's right, okay. I will do that. Colette, I'll do that as soon as I break people out. Wait for it to, I'll arrange it as we do it, and I'll make sure that the three of you are all in the same room. Okay, I'm gonna go ahead and stop share. And I'm gonna go ahead and stop recording.